In this video, we're going to look at some limit laws for sequences. Assume that a sequence an as n goes from 1 to infinity and a sequence bn as n goes from 1 to infinity are convergent sequences such that a limit as n goes to infinity of an is equal to L and a limit as n goes to infinity of bn is equal to m, and c is a constant. Number 1, limit of an plus or minus bn is equal to limit as n goes to infinity of an plus or minus limit as n goes to infinity of bn. But the limit of an, this is equal to L. The limit of bn, that's m. So the result is L plus or minus m. So essentially, limit of a sum is sum of the limits. Number 2, limit of c times an is equal to c times limit as n goes to infinity of an. This is because c is a constant, it passes through the limits, and we just get c times the limit as n goes to infinity of an, and this limit, of course, is L, so the result is c times L. Number 3, limit n goes to infinity of the product an times bn is equal to limit as n goes to infinity of an times limit as n goes to infinity of bn. Now, we know that the limit as n goes to infinity of an by assumption is L, and the limit of bn as n goes to infinity is m, so the result is L times m. So essentially, limit of a product is product of the limits. Number 4, limit as n goes to infinity of an divided by bn is equal to limit as n goes to infinity of an divided by limit as n goes to infinity of bn. But we know that the limit as n goes to infinity of an is just L, and the limit of bn as n goes to infinity is m, so the result is L divided by m. So essentially, limit of a quotient is equal to quotient of the limits. Now, the limit as n goes to infinity of bn can't be equal to 0 because you can't divide by 0. All right, number 5. The limit as n goes to infinity of an to the power of p, bring the limit inside the brackets, is equal to limit as n goes to infinity of an to the power of p. But this limit is just L by assumption, so the result is L to the power of p. Assuming that the exponent p is positive, and also the terms of the sequence are positive, an is larger than 0. All right, let's look at squeeze law for limits of sequences. Let's assume that an and bn and cn are sequences where n is larger or equal to 1. Let's also assume that an is between cn and bn for n larger than some capital N. Now, if the limit of bn as n goes to infinity is equal to L, and also the limit of cn as n goes to infinity is also equal to L, by squeeze law, the limit of an as n goes to infinity is also L. And that's because an is squeezed in between bn and cn. So if cn has a limit L and bn has a limit L, then an's limit also has to be L. Let's show that on a graph. It will be easier to visualize. So you can see how the sequence an, which is in green, is kind of squeezed between cn and bn. And as n goes to infinity, as we increase n, you can see that an has no room to maneuver, so the limit of an is essentially going to be L. So the sequence an is getting squeezed more and more between the sequences bn and cn, whose converging limit is L as n goes to infinity. So for that reason, the limit as n goes to infinity of an is also L. This result is the squeeze law. All right, let's apply the squeeze law to find the limit of the sequence an is equal to sine n divided by n squared plus 1. Our goal is to find two sequences, bn and cn, such that an is equal to sine n divided by n squared plus 1 is sandwiched between these two sequences. So let's start with sine n. We know sine n is between 1 and negative 1 for all n. Now let's divide by n squared plus 1. Why do we do that? The reason is because we can create an equals sine n divided by n squared plus 1, and we can use the squeeze law to find its limit. So divide everything by n squared plus 1, the right-hand side, the left-hand side. There it is. So we now have an is less than or equal to cn, larger or equal to bn. So we're going to label bn to be equal to negative 1 divided by n squared plus 1 And we're going to label an to be the middle sequence is sine n. And this is the converging limit that we're trying to find. And we'll label Cn to be 1 over n squared plus 1. Now, we know that the limit as n goes to infinity of Bn is going to be equal to the limit as n goes to infinity of negative 1 over n squared plus 1. And this is simply going to be 0 because we have negative 1 divided by infinity. As n goes to infinity, the quadratic function n squared plus 1 also goes to infinity, so we have negative 1 divided by infinity, which is 0. Similarly, we can show that the limit as n goes to infinity of Cn equals 1 over n squared plus 1. And essentially, this limit is going to be 0 as well, for the same reason, because you have 1 divided by infinity. So what we have is sine n divided by n squared plus 1 is less than or equal to 1 divided by n squared plus 1, larger or equal to negative 1 divided by n squared plus 1. And the negative 1 over n squared plus 1, we label that as Bn, and this is An, and this is Cn. So taking the limit of everything as n goes to infinity, well, this limit we showed is 0. And limit of Cn as n goes to infinity is also 0. So the limit of this An by squeeze law has to be 0. So basically what we have is sine n. Let me write that a bit neater. Sine n divided by n squared plus 1 is less than or equal to 1 over n squared plus 1, larger or equal to negative 1 divided by n squared plus 1. We take the limit of everything as n goes to infinity, limit as n goes to infinity, and limit as n goes to infinity. We showed that limit of negative 1 over n squared plus 1 is simply 0 because you're dividing by infinity. Negative 1 over infinity is 0. And we also showed that for the same reason, limit of 1 over n squared plus 1 is also 0. That means the limit of an, which is sine n divided by n squared plus 1, has to be 0 by squeeze law. By squeeze law. All right, let's look at another theory. So we have if the limit of an as n goes to infinity is equal to L, and the function f of x is continuous at x equals L, then the limit as n goes to infinity of f of an is equal to f of limit of n goes to infinity of an. So essentially, you're bringing the limit inside the brackets, and that's equal to f of L. All right, but the key is that the function has to be continuous at L. So let's look at an example. Compute the limit of the sequence an is equal to cosine of pi over n as n goes to infinity. Clearly, we can see that the function f of x is equal to cos of pi over x, cos of x, is continuous for all x. In particular, is continuous for x equals 0. So we can apply this theorem. All right, so basically what we have is we have the limit as n goes to infinity of cosine of pi over n. Bring the limit inside the cosine bracket. So we get cosine of the limit as n goes to infinity of pi over n. And we get cosine of, what is the limit as n goes to infinity of pi divided by n? Well, the denominator just grows infinitely to infinity. We get pi over infinity. Result is 0. And cosine is continuous at 0. So cos of 0 is equal to 1. This is the limit of the sequence cosine of pi over n. So the sequence converges to 1. All right, let's look at a few more sequences. So here we have calculated the limits of the following sequences, an, bn, and cn as n goes to infinity. So the first one is an is equal to n squared divided by n plus 1. The second one is bn is equal to square root of 2n minus 1 divided by 4n plus 2. And the third one is cn is equal to sum of 3 different terms. So we have cn is equal to e to the power of 1 over n plus cosine of 2 over n plus arctangent of 3n. Let's look at part A. So here we have the limit as n goes to infinity of an. This is equal to limit as n goes to infinity of n squared divided by n plus 1. Let's divide by the highest power in the denominator, divide by n, and divide the numerator by n as well. So we get n in the numerator, we get 1 plus 1 over n. 1 over n is going to approach 0 as we take the lim as n goes to infinity. N is going to go to infinity, so we have infinity divided by 1 plus 0, which is 1. Infinity over 1 is infinity. So for part A, we can see that this sequence diverges to infinity. So we say the limit of an as n goes to infinity is equal to limit as n goes to infinity of n squared divided by n plus 1 is equal to infinity. We say the sequence n goes from 1 to infinity, diverges to infinity as n goes to infinity. Now let's look at part B. For part B, we have the limit as n goes to infinity of Bn. This is equal to limit as n goes to infinity of root of 2n minus 1 divided by 4n plus 2. Now we know that we can bring the limit inside the square root sign, so let's do that. Bring it inside the square root function. We have limit as n goes to infinity of 2n minus 1 divided by 4n plus 2. This is equal to root of 2n. Let's divide everything by n. Divide by the highest power in the denominator. 2n divided by n minus 1 divided by n, all divided by 4n divided by n plus 2 divided by n. There it is. And now we get root of, and we're taking, of course, the limit as n goes to infinity. Limit is inside this square root. So we get root of 2 minus 1 over n, that's the numerator, divided by 4 plus 2 over n, and we take the lim as n goes to infinity. What does that give us? We get 2 minus 1 over infinity is 0, of course, divided by 4 plus 2 over infinity is also 0. Root of 2 over 4, root of 1/2 is 1 over root 2. So the limit as n goes to infinity of Bn is equal to limit n goes to infinity of root 2n minus 1 divided by 4n plus 2 is equal to root of 1/2, which I can write as root 1 divided by root 2, which is 1 divided by root 2. So we can say that Bn converges to 1 over root 2 as n goes to infinity. All right. So now let's look at part C. For part C, we have limit as n goes to infinity of Cn is equal to limit as n goes to infinity of e to the 1 over n, e to the power of 1 over n plus cosine of 2 over n plus arctangent tan minus 1 of 3n. Now we know that limit of a sum is sum of the limits. So let's distribute the limit across each term. Limit n goes to infinity of Cn is equal to limit as n goes to infinity of e to the power of 1 over n plus limit as n goes to infinity of cosine of 2 over n plus limit as n goes to infinity of arctan tan minus 1 of 3n. All right, so what do we get? We get limit as n goes to infinity of Cn is equal to, now we can bring the limit inside the exponential bracket. In the exponent, e to the limit as n goes to infinity of 1 over n. And for this one, we can bring the limit inside the cosine function, plus cosine of the limit as n goes to infinity of 2 over n. Plus tan minus 1, bring the limit inside the arctan, tan minus 1 limit, n goes to infinity of 3n. So we have limit n goes to infinity of Cn is equal to. What is the limit of 1 over n as n goes to infinity? 1 over infinity, we get 0, e to the 0, plus. What is the limit of 2 over n as n goes to infinity? Well, we get 2 over infinity, which is 0, so we get cosine of 0. Plus, what is tan minus 1 of infinity? Because as n goes to infinity, 3n also approaches infinity. E to the 0 is 1. Cosine of 0 is, of course, 1. What about tan minus 1 of infinity? That's saying what is the angle whose tangent is infinity? And the answer, of course, is pi divided by 2. So the result is 2 plus pi over 2. So the limit as n goes to infinity of Cn is equal to 2 plus pi over 2. So we say the sequence Cn converges to 2 plus pi over 2 as n goes to infinity. All right, thanks.